This is the second video now for section 7.2. We just finished talking about taking partial derivatives with respect to one variable at a time. Marginal analysis is a great way to explain how this is used. Marginal analysis is the approximate change in your function's output, whether it be cost, revenue, or profit, as your variable goes up by 1. Okay, so you're only allowed to increase one variable by a unit while the other variable stays constant from where it was before, right? So for question number 5, you are told that a company is selling swimming pools in 2 sizes. The company's profit is given by a particular f of xy function. We don't know that function, but we know x is how many of the 24-foot pools were sold, and y is how many of the 18-foot pools were sold, okay? And we're going to figure out what the interpretation would be for f sub x of 500, 120 equaling 1500 tells us. Okay, so the subscript x in this location tells you that x is the variable. X is the variable. So x is changing. Okay, x is allowed to change. X is allowed to change. X is allowed to go up. However, y is constant. Y is constant. Okay, so the interpretation is started for you. It says if the number of 24-foot pools sold per year is, what is it going to do? Is it going to change? Is it going to go up, down, stay the same? And the idea with marginal analysis that we learned about weeks ago is that your variable is going up by 1 unit. In this case, x is going up by 1 unit because you're told that this is the partial derivative with respect to x, which means x is your variable. X goes up by 1 unit, okay? So we're going to mention that in our description. If the number of 24-foot pools sold per year is increased by 1, you know what, let's make it even better. Increased from 500 to 501. Right? If it's increased from 500, because that's where you took the partial derivative when the value x equaling 500, so it goes up by 1 unit, which is to 501. What happens with the number of 18-foot pools? That's the variable y. Is that one going to change? Is that one going to go up from 120 to 121? No. Y is treated as a constant. So the number of 18-foot pools sold per year is held constant at, how many is that? 120. Okay. The profit will, what's it going to do? Well, it's going to increase because your output is positive. Increase by $1,500 for that year. So you increase the number of pools sold by 1 extra for the 24-foot size. However, the number of 18-foot stays the same, held constant at 120, your profit's going to go up by $1,500 just from that sale of the 1 extra larger diameter pool. All right, in this next example, you're given information about selling 2 kinds of hammers, brand X, brand Y, brand A and brand B, my bad. If brand A is sold for X dollars, brand B is sold for Y dollars, the monthly profit is given in terms of this profit function, P of XY. All right, interpret the meaning of the output, or this entire statement, I guess. Interpret the meaning of that statement. Okay, so you're told that the variable here is Y. Y is the variable, Y is the variable, and so that means that X is the constant. X is constant. All right, so if the number of brand A hammers sold per month is, okay, is brand A going to change? Is it going to go up? Or is it going to stay constant? Now, brand A was your X variable, wasn't it? Brand A said sold for X dollars. So if you keep that price the same, which means stays constant, held constant at $27, because we're in terms of dollars for these variables. What's happening with brand B? Brand B hammers sold per month. What's going on with that variable? Brand B is your Y variable in this case. Y is the price of the brand B hammer, and so this one is allowed to increase. Increased by from $10 to $11. Okay, we're going to go up by $1. Goes up by 1. What's happening? The profit will, this time your profit's going down, isn't it? It's going to decrease by how much? By 20, oh, my bad. Hold on. Decrease by $4.50 because my output was negative 4.5. So it's going down because it's negative, and it's going down by that quantity. Now, one thing that I needed to check that I did not, let's go ahead and write here, your units on profit. Your units, let me highlight it so you can see it. Your units is in hundreds, monthly profit is in hundreds of dollars. So we have to say decrease by this many $100. Not $4.50, by that many $100, which means, or what is that? $450. Okay. Just by moving that decimal point over 2 places, you convert from $4,500 into 450 straight dollars. Okay, so for example 7, we are actually given a function Q of K, L. The problem says, a manufacturer estimates that the annual output at a certain factory is given by the function Q, where K is the capital expenditure in thousands of dollars, L is the size of the labor force in worker hours. So K is in thousands and L is in hours. Part A, find the marginal productivity, that's Q, of this capital with respect to K. All right, so marginal productivity of capital means that capital is your variable. Capital is the variable. And then the marginal productivity of labor. So then labor is your variable. 2 separate problems here. When the capital expenditure is that and the labor is that. Okay, so we first have to find the partial derivative of Q with respect to K. In other words, L is held constant. L is held constant. Go ahead and highlight that for you. L is held constant. So the derivative of Q with respect to K is going to be 30 times 0.3 times K to the, what is that, negative 0.7? So that's 0.3 minus 1. L doesn't change because L is a constant. And then you want to specifically calculate this amount, productivity amount, when you use K equal to 630 and L is equal to 830. Right? I'm not using all of the zeros on 630,000 because K is in terms of thousands already. You work it out, plug in the appropriate numbers, you're going to get the answer of 10.92. Take a few minutes, pause the video, check that out. And what are we in? Units. Okay. So that's the change in the productivity. When the variable K is changing, it'll go up by 1 unit. From 630, it would go up to 631. With that change, your productivity would increase by 10.92 units. All right, let's check out the derivative of Q with respect to L. In this case, we're going to use L as your variable, and therefore K is your constant. That's your constant. All right, so the derivative is going to be 30 times 0.7. Bring that 0.7 down in front. Repeat it. Repeat all of the constants that were there. But the variable L is going to be raised to the negative 0.3 power because that's 0.7 minus 1. And now we evaluate this derivative function at the values, same as before, 630 for K and 830 for the number of hours. And if you plug in those numbers, you should get the answer 19.33 units. Pause the video, make sure you can get that. Part B, should the manufacturer consider adding a unit of capital or a unit of labor? In other words, do you want to increase the capital or the labor? Because you can't do both. So the question goes like this. Compare these two increases in productivity. Marginal analysis tells you how much your output goes up or down as your variable goes up by 1 unit. So the first output told you that this is your increase in productivity if K goes up by 1, okay? So if you go from $630 to $631,000 in capital expenditure, the increase in productivity is 10.92 units, all right? Over here, you're told that if L goes up by 1 unit, then the increase in productivity is 9.33 units. So you get a bigger bang for your buck over here when we increase L because 19.3 is bigger than 10.9. So for that reason, we would like to increase labor by 1 unit. So it's going to go from 830 worker hours to 831. The increase in hour that we have to pay somebody to do with their salary is worth it. We get a bigger bang for our productivity buck by increasing labor than if we would have poured more money into our company with capital expenditure. Since 19.3 is bigger than 10.92. Okay, we get a bigger bang for our buck because 19.33 gives you a higher increase in productivity than 10.92. Okay, let's check out number 8 and then we'll take a break. Suppose that a company produces 2 styles of baseball uniforms. We've got the modern, we've got the throwback. It's estimated that if they produce X modern styles and Y throwback styles, those are both quantities, the total profit is given there for you in terms of dollars. Find P of 125, 200, interpret its meaning. No surprise here, you're just going to substitute the value 125 in for X, the value 200 in for Y, and if you want to take a minute to check this out, you should get $353,750. Part B. Now you're going to look at derivatives. So find the derivative of P with respect to X, which means Y is your constant. So let's see if we can do it without the highlighting. X is your variable, Y is your constant. X is your variable, Y is constant. X is the variable, Y is the constant. Okay, so something like this. I filled in with zeros so that you can see exactly how each term falls out from the derivative, but you don't need those. That's what it looks like without the zeros. Plug in the value 125 for X and 200 for Y, and you end up getting 5,700. All right, so interpret your answer, right? So if you increase modern from 125 to 126, and leave throwback at 200, profit will increase by about $5,700. Part C says, now find the derivative with respect to y. So the derivative with respect to y is going to look like this. And plug in the value to 125 for x and 200 for y. You're going to get the answer negative 350. All right, so interpret the meaning of that result. This time we increase the throwback production from 200 to 201. And we leave modern alone. Leave modern at 125. The profit this time goes down because it's negative. Decreased by about $350. That's no good. So that's a couple of examples there for interpreting the output values that you get from the marginal productivity equation.